All right. Happy week 8, everybody. Happy winter. But you can watch winter melt. Just get in. Those of you in the back will have a really nice view of winter melting. So here's the plan for the week. We're now in the 4th part of the course. I'll say a little bit about that in a second. Today we'll do 4.1. Thursday, I said 4.3 and 4.4. Really probably just 4.3. Homework help is a slightly unusual schedule because I'm no longer free Wednesday evenings. So I can do 5 to 6 on Wednesday, but can stick around a little bit after that, but not much. I thought to add a time Tuesday afternoon. I may shift this if people would have a strong preference. And I can stay longer if people need to, but I thought, since it's early in the week, try for half an hour and see how far that gets us. I've left some times off. And Mackenzie is 4 to 5:30 on Thursday? OK. As usual, if these times don't work, let us know. We'll figure something out. The homework this week, I think, is not shouldn't be anywhere near as long and certainly not as algebraically intense as the one that you did for Friday. I think that's it in terms of announcements. Any questions, logistical queries? OK. So thus begins Epoch 4. So the last chapter was all about shortcuts, chain rule, product rule, and taking derivative of the sort of building block functions, trig functions, power functions, exponentials, and logs. And chapter 2 was about what the derivative is and what it tells us. And in this chapter, we put those two ideas together, and we start actually, we know what the derivative is, and we know how to find it, and so we put that together, and we start doing stuff with it. So that's Epoch 4. And I want to start by reminding you of a few things from chapter 2, and then introduce a little bit of vocabulary and some terminology, which I think is fairly intuitive, not anything too complex, and then just start doing some examples. So I suspect the trajectory of today, I'll probably do I hope it's not too long, but maybe 15 minutes of sort of introduction and getting us oriented to a few things, and then a bunch of examples that we'll work through sort of step by step and see what issues arise as we do that. So we're now actually using derivatives, right? You've been finding derivatives for a long time, and then you just say, "Yep, here it is." And you might wonder, why are you doing this? Now you know. OK, so using derivatives. And the answer is that derivatives are useful for figuring out all sorts of stuff. So first, some reminders. If f of prime is positive, what does that tell us about a function? It's increasing, yep. F is increasing. And if f prime is negative, it's decreasing. What about if the second derivative is positive? What does that tell us? Yep, f is concave up. Excellent. And OK, so that's stuff we worked with in chapter 2, but haven't really thought about as we've been having fun becoming friends with the chain rule. So now we get to think about that again. So what we're going to do is use these ideas and the mechanics of taking derivatives to analyze some functions. So let me introduce some terms. All right, so analyzing. So this might be some function f of x. And often we might be interested, whoops. in knowing what this point is, when we're at the top of the mountain, or when we're at the bottom of the valley, or when we're at the top of this mountain. And so those types of points, those are known as critical points. And this would be called a local maximum. Maximum because it's a maximum. Local because it's only the maximum locally. So this point, if you go to the left or right, you're not as high as you were if you just stood here. But it's not the overall maximum of the function. There's a higher mountain top over here. You will not be shocked to learn that this is a local minimum. Minimum because it's a minimum. Local because that's only true locally. I don't really know what else to say about these. This is sort of exciting. It's local, and it's a global max, ELOB. Local because if you wander to the left or right, you're going downhill. But it happens to be the global max as well because it's the tallest mountain peak. Okay. If you're at a local minimum or maximum, what do you know about the derivative? Yeah, so when we're right here, the function momentarily levels off. I'm drawing on little tangent lines here. So I should write that down. So at local min or max f prime x equals 0. So this is sort of exciting in that that's a statement that we can do some algebra and calculus on, and we could do things like solve for x. If you wanted to know exactly where is this local max, where is this local min, we now have a procedure that we could carry out. We would take the derivative, set the derivative equal to 0, and we'll have a local minimum or local maximum, or maybe something else that I'll mention in a second. We're good? We're good so far? This is not tremendously deep terminology. Yeah.
I'm assuming that you can also have the local and global minimum?
Yes, you could, although this function doesn't have such a one. Yeah. If you turn this upside down, then you would have a local and global min. Yep, good. OK, so this terminology is not particularly deep. Let me introduce a little bit of terminology that's also not particularly deep, but maybe not as slightly deeper than this. OK, so if f prime x equals 0, we say that x is a critical point. So that's just a little bit of jargon for points where a derivative equals 0. And not all critical points are mins or maxes. There's another type that's worth mentioning, so note. So this function has a critical point here, because the slope is 0, but it's neither a min nor a max. OK. I don't think so. In multiple dimensions, they're sometimes called saddle points, but I don't know that they have a name. I was thinking about that as I was writing that. I can't think of any. I'll check in the book, but I think it's just called neither min nor max. I know that's really boring, but. OK, let me mention one more little bit of terminology, and then we can just start putting this to work and doing some examples. So all of this has been about the first derivative. We're looking where you find the first derivative, figure out where it's 0, solve for those points, and we get local maxes, local mins, maybe global maxes, global mins, or maybe none of the above. The other thing we might want to do to analyze the function is look to see where the concavity changes. And a point where the concavity changes is called an inflection point. So points where concavity changes. And that means that the second derivative changes sign. So right around there where I drew the arrow, we go from concave down to concave up. And so you'll say that's the inflection point. And figuring out inflection points can be useful for graphing functions, and sometimes they might have meaning maybe where acceleration changes, where growth rate starts slowing down. And calculus tells us how we can find those points as well. So at this point, you have all the tools you need in your toolbox. You know how to calculate derivatives from Chapter 3. You know how to think of them geometrically. You've learned a little bit of not very deep jargon. So we're just ready to start going for some examples. You may not look ready, but I believe you are ready. So let me say a couple of things about this example. In these problems, you're analyzing functions, and you're going to take a derivative and a second derivative, and you're going to sort of be shuttling back and forth between derivatives and their functions and their derivatives. It can be helpful to write out a little bit more. I'm trying sort of to model that here. So to find the critical point, we need to take the derivative, set it, set. That was an elision in some language other than English. Set f prime equal to 0, and then solve for x. So here's the derivative. Then I set the derivative equal to 0, and then I'm reminding myself that I'm solving for x. So again, writing out that little phrase, solve for x, can remind you what you're doing and help these notes be more intelligible when you're looking at them later on. So I'm doing that, and then here I get a critical point. X equals 3. So the problem asks not only for the x value, where horizontally that critical point occurs, but how high the mountain is. What is that maximum, or it turns out to be maximum value. So to get that y value, you need to plug this back into the function. So y for that critical point is f of 3, and I plug in 3 to the function, and I got 4. Yes?
So the critical point is just x value, and the maximum is y value, or is it coordinate?
I guess I would say it's probably the so I'm just trying to think, how do I sort of use this? The crew.
What are they asking for?
Let's see. Well, they was me, so I should know. So I guess I would normally say that like this function has a critical point at x equals 3. I'm just thinking how I'd use that vocabulary. But and then if you wanted the coordinates of that point, it would be 3, 4.
So that's the local maximum.
Exactly, yeah, yeah, yep. All right, so here's our critical point. And then, let's see, we also need to ponder inflection points. So inflection points, that's when concavity changes. That's when the second derivative would change sign. So we're going to need the second derivative. So let's calculate the second derivative. Oh, and I did that over here. So the second derivative is just the first derivative of the first derivative. The derivative of minus 2 plus 6 is minus 2. We'll say, well, this is sort of boring. Derivative is always negative. So it's always concave down. And if it's always negative, it's not changing sign. It's always negative. So there's no inflection points. So at this point, you can make a sketch of this function. You know it has a critical point at 3, 4. And since it's concave down, then this must be a maximum. You also know that because this is an upside down parabola, the leading term in this polynomial is negative. So it'll be negative for large x. So it may be at some point in your life, it probably would have been in pre-calculus, maybe algebra 2, you might have had to memorize the formula for the vertex of a parabola. In the unlikely event you still remember that, you can forget it immediately because you can derive it. I mean, that's what you just did without having to think about a formula. You just calculated the derivative, set it equal to 0. So one little bit of memory freed up from pre-calculus. I remember having to memorize that A, B, C, something, something, I don't know. But now with calculus, you don't need to memorize it. You just figure it out. Calculus is cool that way. So let me mention, maybe I'm going to do that over here. One other thing sort of prompted by this example, and then I'll stop talking and we can go back to doing this stuff. So in these sorts of problems, you'll take the derivative. You'll find the critical point or critical points by setting the derivative equal to 0 and solving for x. And then you'll need to classify those critical points. So there are a number of different strategies or schemes for doing that. I should say what this list is. How to tell the type of critical point yeah. So what might be some strategies? What might you do?
Plug in numbers next to it.
Yep. So you can plug in numbers. See if y increases or decreases. Yeah.
By what top of critical point you mean if it's a local minimum or maximum?
Correct. Exactly. Yep. Yeah. What else could we do to help figure this out? Graph it. Yep. So feed it into Wolfram Alpha or one of those calculators you lug around, and just see if it's going down or up. What's something else we could do? Look at the concavity. So look at so if the concavity is negative, what type of critical point is it? It's a max. If the concavity is positive, it's upward, something like this. It's a min. And what if the concavity is 0? If people are sort of saying, I don't know, that's correct. You can't tell, or I guess inconclusive. So this is sometimes called the second derivative test, which makes it sound much more formal than I think it has to sound. And it sounds like something you have to memorize. But again, if you know what concavity is, which you do, you know what concavity is, you can just sort of picture this and saying, oh, if I've got a critical point in a region where it's concave down, it has to be a max. Here's a region where it's concave up. If I've got a critical point, it's got to be a min. I would say in practice, 90% of the time, you can just make a graph with a reasonably reliable bit of technology, and it's pretty clear what's going on. There might be times when you want to double check, or you're not sure, or you need to calculate inflection points, in which case you'll need to do all this stuff. But anyway, all three of these are perfectly legitimate ways of finding out what type of critical point you have. So let's now think about this graphically. That's what problem 2 will do. And then we'll do 2 more examples, problem 3 and 4, that will be more interesting functions than this one that we started off with. But anyway, give number 2 a try. We'll talk through that, and then we'll launch forward into 3 and 4. So let me say one thing about this problem, and that is to sort of think about critical points and inflection points before you make a sketch of the graph. And if you want to think about making a sketch first, that's fine, but this will maybe give you another way to think about it. So a critical point, that's a point at which the derivative is 0. So this is a graph of the derivative. So where the derivative is 0, these orange circles, those are the critical points. So then we need to classify those 3 critical points. And how would you think about, say, this one? Min, max, or neither? All right, I heard the half-formed syllables of min, max, and neither. So that's good. It's good we're discussing this. So yeah, this will be a maximum. So a couple ways to think about it. Here the derivative is positive, so you're increasing. So imagine you're walking along, and you're going up a hill. And you're going up a hill, and then here you're going down a hill. The function is decreasing. So this would be a max. Another way to think about it, the slope of the first derivative is negative. That means it's concave down. So it's going to look, well, let me draw it up here. All right, so concave down must be a maximum. Let's jump over to this one. What about this one? Min, max, neither? Min. This one's a min. So you're decreasing, and then you're increasing. That's what happens when you walk through a valley. You're decreasing, and then you're increasing. The derivative of the derivative, the second derivative, is positive. So this would look like that. So it's concave up, so that means you're at the bottom of the valley. What about this one? This is a neither one. So here you're decreasing, and then you momentarily level off, but then you're decreasing again. So this would look like, well, something like that. So you're losing money, you almost stop losing money, and then you start losing money again. So it levels off for just a second. So this would be neither. Inflection points occur when the second derivative changes sign. So the second derivative is a derivative of the derivative. So that's where the first derivative goes from decreasing to increasing, right? Here's the change. It was decreasing, now it's increasing. It was increasing, now it's decreasing. And it was decreasing, now it's increasing. So those would be the 3 inflection points. And then one can sketch the functions. I'll do that in a second. But I wanted to sort of zoom in on those points to think about them one at a time. Other questions on that? I feel like this is a situation where I almost feel like saying aloud, you're increasing and then you're decreasing, then you're increasing, almost makes it worse than if you just sort of look at it and try to see the shapes. I mean, if hearing me talk or talking yourself like that is helpful, by all means do it. But it may be the case that, I mean, the whole point of the picture sometimes is we don't need to use words. So anyway, there'll be a couple practice problems like this on the homework. The last 2 problems that I want to do, and I'll complete a sketch of the functions, but I want to give myself a little more room to work in, are a little more interesting examples than this, and I'll have a few surprises in them, and I'll have to kind of work through. And I'll probably also fire up Wolfram Alpha and make some plots up here to help us through those. So give problem 3 a try. It's not as straightforward as problem 1. And it might be fun at first to sort of just guess, take some very general guess about what you think that function is going to look like, and then you may be in for a surprise. So let's start by plotting the derivative. So this is a cosine function. Those are wiggly functions that start at 1, go down to -1, go up to 1. But now we're shifting it up by 1. So instead of going between 1 and -1, it goes between 2 and 0. So this function is going to look like this. So right away, what does that tell you about the shape of h?
It never goes below when x is positive. It never goes below 0. It's always increasing.
Right. Yeah. So the derivative is always positive, except for these little instants where it's 0. So it's always increasing, which is perhaps a little disappointing because when thought for sure, I mean, I don't know. I look at this and I think that's got to be some cool wiggly thing. It actually doesn't really wiggle. It never decreases. It's always going up, except it levels off just for an instant. So let's see. This is going to so it's increasing, levels off, critical point. But then it increases again. I probably should have. Slowly, then quickly, then slowly again. Looks like it's going to level off. Oops, but then it increases again. So it's going to keep going up and up. This would look like so it is sort of wiggly, but it's actually it never goes down.
Like a stair.
Yeah, it's sort of a staircase type of thing.
The critical points are the one where the h of prime axis.
Yep. So these are all the critical points. And they're all these neither min nor maxes. OK, so this is sine x, and the minus flips it upside down. So sine normally starts at 0 and goes up. This time it starts at 0 and goes down. Boy, let's see if I can do this. OK, that's not the most uniform of sine curves, but maybe it gets the point across. So So we'll have points of inflection where the second derivative changes sign, where we have a change in concavity. And so that's going to be, right, we're going to have a change in concavity here. Then we're going to go from up to down here, and then here, and then so on. So to keep with the color scheme from before, these are all the inflection points. So the concavity is changing: concave down, concave up, concave down, concave up, concave down, concave up, and so on. So we get lots of points of inflection, but no mins or maxes. So for a lot of these, you'll want to plug these into a calculator or computer and get a graph. But the goal is to not be completely reliant, not to totally outsource your intuition to your computer or calculator. But when you get a shape like this, which is, I think, counterintuitive, I wasn't picturing this when I see x plus sine x, again, I think for sure it's going to have to go up and down. But then when there's something surprising, you might say, oh, did I do this right? Did I do this wrong? You now have the means to think about shapes using derivatives and second derivatives. So I'll show you what Wolfram alpha does for this, just in case you want to see it in a moment. But let's wrap up by doing problem 4.
But what about the x and y values? The x for x and y values.
Oh, and you want me to do more than just point at them on a graph?
Like, are we supposed to find numbers?
I guess okay, so you could find numbers. I would say for this problem, I would be content with just being able to label them on a graph. So rather than go through the algebra of how you would write all this stuff down, the main intention of this was for this to sort of be a graphical one. So.
There's also like infinitely many,
Right, they keep going. Yeah, so the points of inflection would be x equals n pi for an integer n. And I think this is going to be maybe also n, 2n. I'll have to. This is 2 pi. This pi. 2n pi. I'll have to. Let me think about how to do this one. I think because this sign is so non-uniform, I'm not seeing how it lines up with that. But anyway, if you had to do it for this one, that's sort of how you would do it. But the main thing is the main goal of this was to just sort of think conceptually and graphically to get to this shape. All right, so let's end by doing problem 4. So again, find critical points, classify them, find inflection points, and sketch the function. And we'll end by doing this on a computer. Let's go back to the sine one. Here's a plot of that function. I plotted from 0 to 4 pi. Could do it in a larger range. And there it goes. Looks like it's going to decrease. It never does, so it's a wiggly little staircase thing. We could plot. Let me go back. Let's see. 1. The excitement builds, although this one isn't so exciting. There it is. Yep. So this was a derivative. It goes between 2 and 0. So it's always positive except for these little instants where it's 0. So for this one, for number 4, g is x e to the x. I take the derivative. To find critical points, I set the derivative equal to 0, and I solve for x. So here I am doing that. I get x equals minus 1, which I turned momentarily into plus 1. But there was sufficient protest that I turned back into minus 1. So then this would be the y coordinate for that. The main thing is that it's negative. and here's a negative coordinate for that. Then inflection points, similar thing, but we play the same game but with the second derivative. So I take the second derivative. Here it is. I set the second derivative equal to 0. I solve for x. And find x equals -2.
Do we need to find the y value for this?
I guess one could, but I didn't feel like it. So now we have a function with one inflection point and one critical point. We might want to know what does this look like. And so we could feed that into Wolfram alpha. And one of the things that this type of analysis can be useful is it tells you where the interesting parts of functions are. So and that interesting, I guess, is a rather qualitative idea. But things are interesting when there's a critical point, where it turns around, or where there's an inflection point. And Wolfram won't always find the interesting parts for you. So if you just ask Wolfram to plot x e to the x, because you think, I have no idea what this looks like, and let's see, it would give you this. And your eye might be drawn towards this pretty serious exponential part here. It's an exponential with an extra x, so it's exponential and a little more. And you might not notice that there's maybe something interesting going on down here around -1 and around -2. So we can use the work we did there to give us a better picture. Let me set the range from x equals, let's say, -3 to +1. And again, the excitement builds. It's weird to me that it calculates the length of the curve faster than it calculates the curve itself. But anyway, OK, so now we've just zoomed in, and we can see what we just calculated here. So there's a minimum at -1. And it's a little hard to see, but not impossible, that the concavity changes at -2. So here it's concave up, and here it's concave down. Let me, maybe that will be clearer if I did this. There we go. That's a little clearer. You can see concave down switches to concave up. And then here's the critical point, which we can see is a minimum. So lots of different ways to see this. I think when actually doing math or using math for something, whatever that might mean, this is a pretty typical mode. And I think if you can sort of shuttle back and forth between doing a few simple calculations, solving a few things, letting that guide you for how to use technology smartly. So not just plug it in and say, make a function and hope it gets the interesting limits correct. And you can then sort of check. If you say, hey, I think there's an inflection point here at -2, that's something you should be able to see in a graph. So you can dial the graph up, and you can see if you can see it. If you can't see it, that means either you did it wrong or you typed it into the computer wrong. So for a lot of these problems, I would say, sort of rather than like memorizing the second derivative test, I just think using common sense and a good graphing calculator or Wolfram alpha and sort of shuttle back and forth between these two modes is definitely the way to go. One other thing I want to mention, which I've mentioned before, but just to remind you, in terms of there are two parts to the final that's coming up in 2 weeks. One of them, the part that's you can't get help on and is like the midterm, is only chapter 3. So the problems in chapter 4, I think, are harder. I hope also more interesting, but they're not the sort of things that you're going to be expected to do on the final. The part of the final where you can't talk to other people. Exactly. Yep. So we'll continue with this sort of analysis next time, and we'll do some optimization problems.